Hello, I am Dr. Sri Banerjee, and in this video I'll be going over one very important epidemiological tool, which is key in clinical settings, but also really I would say is in the intersection between understanding and articulating information within the realm of epidemiological setting, but also within the setting of healthcare and the clinic. So this is an important measure, and the name of this is number needed to treat. This is actually a value, number needed to treat. It's something that when I was in the clinic and seeing patients, a lot of times when pharmaceutical companies came and were, say, providing information about a new antihypertensive or a new clinical trial on a cancer drug, this was information that we were interested in because it was really important to know how efficacious a certain therapy is when it first comes to the market. So let me explain this a little bit more. So the main epidemiological measures, just to emphasize that within this slide that we're going to be going over, is the absolute risk measure, the relative risk measure, and then the number needed to treat. So let's start off by some basic definitions and build our way up. So just thinking about what absolute risk reduction means. Basically, it's the proportion of patients or individuals within the community if you're building an intervention, public health focused. So it's the number of patients who are spared the adverse outcome as a result of having received the experimental rather than controlled therapy. So if you're talking about some sort of intervention, it could be even behavior change, maybe some sort of smoking cessation intervention. So that's, of course, risk reduction. So in terms of the relative risk reduction, that was absolute. That is how much the treatment reduced the risk of bad outcomes relative to the control group who did not have the treatment. So one is absolute and one is relative. So now that we have talked about risk reduction, if you take the reciprocal of that, then you get number needed to treat. And this is basically another statistical measure which was determined. I mean, this was, when it was first discovered, really key in understanding this. And the reason it was so important is because it compared the consequences of the intervention and no action. This was one way that this could be done. The second advantage of this statistical measure was that it could help gauge the potential adverse events or harm that is associated with interventions. So just the recognition that there may be harm and how to quantify that. And then finally, allowing a measure or comparison of the treatment methods where the repercussions of one intervention in the diagnosis, treatment, or prevention of the condition may be weighed against other interventions. And so one of the studies that I go over within this presentation is in fact a comparison and not an actual randomized controlled trial. So these are some variations of what classically we think of number needed to treat is useful. So eventually, what is the objective? But the objective is to allow health practitioners, whether they are clinicians or public health practitioners, to be able to discuss with patients and community members treatment options and focus efforts where they're needed. So this is really a nice, tangible, concrete way to translate research that you may have gotten from your findings, and then how to transform that into a way that people will understand. So the next question that might be going through your mind is that, is this something that people bother about? And the reality is yes. Number needed to treat is in the last 3 decades have just they have just expanded to the point that it's being reported a lot more frequently. So yes, this is something that is important to focus on. There was some good conversation, and I want you to kind of look through the arguments that were made in promoting the use of number needed to treat. So you can kind of go through this. The initial authors had a response, and this is also a good place to look at how people present findings, research findings, and then have responses and provide kind of conversation and dialogue. So this was, again, another response to number needed to treat and the importance and potential pitfalls. Now, remember when the pandemic was taking place, we were still in 2021 trying to determine the efficacy of various vaccines. And so one of the vaccines that was tested was the Moderna vaccine. And I remember when the trial first came out in the New England Journal of Medicine, there was a lot of hype and really a lot of excitement that we were turning the corner, and this was the panacea. Of course, since then, we've needed more boosters, but definitely has proved to be one of the most effective way to prevent transmission of the virus. So the reason I'm bringing this paper up today is I'm going to use this in this video to illustrate some really important clinical measures like number needed to treat. So let me explain this a little bit more. So I wanted to bring your attention to this specific figure within the paper that I presented. This is the vaccine trial, and the findings show that on the right-hand side is the placebo. So individuals that didn't get the Moderna trial, that didn't get the vaccine, those individuals, 185 of them actually contracted the virus, whereas in the Moderna group, there were only 11. So the question that is really the central question is that what is the number needed to treat? What is the number needed to vaccinate in order to prevent another infection? And I'm going to give you a clue. The answer is going to be around 200. So I'm going to show you the steps needed and taken to get to the solution. So the numbers that we're going to be interested in, I'm going to go ahead and highlight. Just so that when you go to the next slide, you kind of have that in the back of your head. So then let's go to the next slide. Now, if you remember just from the previous slide, the numbers, and what I've done here is I've designated these boxes, but this is actually a template that I would like for you to use from any clinical trial. You can use this anywhere and be able to calculate these numbers. And when you get really quick at doing this, it becomes a lot more second nature. So when you begin, it kind of takes more steps. So just for example, we can quickly go through this. People that contracted the virus and received the Moderna vaccine, that's 11 people, and so that was people that didn't get the virus, of course, was 14,123, and so this decimal is considered the experimental event rate, and then this is the control event rate. So just going through the calculation again. So the control event rate, you take that, you subtract out the experimental event rate, and just in the middle here, the relative risk reduction is actually 94%. And for those of you that was following the efficacy percentage, does that percentage seem familiar? If so, it should, because that was kind of the efficacy rate. That was something that the public knew. Then what you do is find the absolute risk reduction. And so this is absolute risk reduction. And then the reciprocal of the absolute risk reduction is the number needed to treat. So there you have it. The estimated number needed to vaccinate with Moderna instead of placebo during the study period would be about 200 to prevent one additional case of documented infection. So what I would like for you to do is, if you can, go and look in the subgroup analysis. And what was interesting in the subgroup analysis when that was taking place is that there were higher infection rates within age subgroups and others. So now what I would like to go over is an exercise which is a different group than what we looked at. So what did we look at initially was all patients. And so while that was revealing information, I think what would be more interesting and important is to see if in subgroup analysis, like individuals who may have a lower immune system, do they also fare as well with the vaccination as the general group? So how would we even begin to try to determine this? And so that, again, setting this up for considering the absolute risk reduction and then the number needed to treat, that will be the best way. So just thinking about how to determine absolute risk reduction. So if you think about the control group, the EER and the CER. So this is where what you can do is take this fraction, and then so the fractions are already available. So take these and then kind of calculate them against each other, and then go from there. one of the premier websites and journals that research is published in, especially as it pertains to medicine or public health, is the New England Journal of Medicine. And here, the main research article that you'll be focusing on is the comparative effectiveness of basically of one sort of vaccine over another vaccine. So really comparing the effectiveness of the COVID vaccine, since as we were in the pandemic and while we were in the pandemic, it was really important not only to measure the effectiveness in the general population, but also look at subgroup analysis and it kind of see how effective it is. So the website that is provided here links you directly to the article that we're going to be looking at in here. So what I'm going to do now is kind of switch gears a little bit and then try to provide a brief synopsis of how you can calculate this as well. So let me get the marker first. So the first thing that we are interested in here is knowing kind of the absolute risk reduction. So how do we calculate that? So the absolute risk reduction can first of all be broken down even further. So you want to first figure out the event rate. So let's look at event rate. But you're actually interested in two types of event rates. Usually one within the control and one within the experimental group. So I'm going to kind of write control and experimental here. So then what you're looking for is really the rate that's needed in each one of these. So if we break that down into rate, so what I'm going to do, because we're not looking at control versus experimental group, we're simply looking at hospitalizations. And the number that we're after, instead of number needed to treat, what is the number needed to prevent an additional hospitalization? So let's look at the percentages again. This will be the control group will designate as the BNT group. So this is BNT. And so for BNT, the rate that is provided here for hospitalizations is 102 out of 152. So what the 152 was by adding these two values. So BNT, the rate, the event rate would be 102 over 152. And then the experimental group we're going to designate as the mRNA. And so that rate is 50 over 152. So you then take these, and you can actually calculate these, by hand, and then that will give you, subtracting the two values will give you the absolute risk reduction. And so simply by taking the inverse of absolute risk reduction, you are given the value of number needed to treat. So I'm just going to write number needed to treat, and I'm just going to use shorthand for everything because of the limited ability. This is another way to designate inverse, raised to the negative one. So then there you have it. That's how you calculate number needed to treat. And I know this might have been confusing, I just kind of scribbled my calculations to the left, but this really shows you how easy it is and quick it is to convert something that really there's a lot of different fractions and percentages going on in ratios to something that is more discernible and easily understood by you and I. So if you want to go ahead and take what we did in the previous example and kind of expand on that, you're more than welcome to kind of fill out what goes in each box, and then accordingly determine what is the final calculation. All the information that you need to fill out this box is available within the body and content of the paper that I have provided. So I encourage you to go back, take some of those numbers, and then calculate that here. I hope you've learned not only how to calculate number needed to treat, but then take that, go back, and so in our example, if you did everything correctly, the answer is 3. So the answer is that you would need to vaccinate 3 people to then make a difference in the effectiveness. So that's when you start seeing the difference in the effectiveness between the 2 vaccines when you treat 3 people. You can also calculate number needed to harm from the same sort of calculation, but that would be when you're measuring like side effects for certain drugs. For instance, spironolactone is a powerful sort of drug used for many purposes, but one of the key sort of side effects is gynecomastia. And so in terms of determining how many patients need to be treated in order to see the side effect, then that can be actually indicative of something of a negative effect. So you can see that the same measure can be used for many different purposes. I hope this has helped not only in articulating this measure, but contextualizing it in the framework of other epidemiological measures. Thank you for listening. So this is kind of a bonus slide where I've provided a lot of different numbers for examples in the a template on how to complete number needed to treat. So this is a comparison. If you go back to the paper on the Veterans Administration and efficacy of the vaccine, comparing 2 of them, this actually goes and looks at a different group. So you can follow the calculations here and practice doing this on your own, so that you can see how this is done, but I wanted to bring to your attention that this top portion, the calculation is different from the bottom portion. So ideally, what you calculate here at the top, the numbers should carry over, but due to the difficulty with the denominator, it was more difficult to determine. So the best way to calculate this, and the most direct way, is to take the actual event rate per 1,000 persons, and then determine what the final number is. And the final number was 813. So this is another one that you can look at from the second New England Journal of Medicine paper. Thank you for listening.